So first of all, we have a system of units, the SI base units here, which I've listed on the board. Now, these are not all of the base units. These are just the most common ones that we're going to use, certainly in chemistry and physics and other classes. There are a few other base units I'll mention as well, but these are definitely the most important ones. So the most important units that we'll probably use in everyday life are the units of length. And the unit of length in the SI base unit is called the meter. You know, you hold out a meter stick, it's about the width of your arms extended. That's roughly what a meter is. And then we have a unit of mass called a kilogram. All right, kilogram of mass is something you can comfortably hold in your hand. The unit of mass is related to how much of a substance you have, also taking into account the type of atom it is. So a copper atom has more mass than a hydrogen atom, for instance. So it's the number of atoms and also the amount of atoms, because of course the heavier the atom is, of course the more mass it has. And then we also have temperature. Now in everyday use, we typically use Celsius. In the United States, sometimes we use a Fahrenheit temperature scale. We never use Fahrenheit in chemistry or physics, almost never. I mean, we kind of use it occasionally, but it's very rare. Usually we use Celsius, but the actual SI base unit of temperature is called the Kelvin unit. And we're going to talk about that in its own lesson later to get you comfortable with what a Kelvin measurement is in terms of temperature. Then we have time. Time is measured in seconds. Doesn't need much of an explanation, just regular old seconds. And then here is another base unit, which is the amount. I should have put the amount of a substance. And in chemistry, we use it a lot. It's called a mole, and it's abbreviated MOL. All right, I don't want to get into what a mole is right now. We're going to have an entire lesson down the road on what a mole is. But you need to know that 1 mole is basically a number to count the number of atoms or molecules that we have. So a mole of a substance is basically a very, very large number. We'll write it down later on the board that expresses how much, in terms of how, not the mass, but the amount of the substance you have. How many atoms do you have? How many molecules? If you could count them with little tweezers, then a mole is telling you the amount of a substance in terms of how many atoms or molecules you have. We're going to get into that a lot later. Now these are called the base units. So length is meters and mass is kilograms. Time is in seconds. Those are extremely common. We use them in chemistry and physics. Temperature is in Kelvin. Amount is the mole of the substance, the counting the number of atoms, basically, or molecules. All right. There are a couple of additional base units that I didn't write down because they're not that, we don't need them yet. One of them is called the ampere. That's the unit of electric current. You might have heard of amps, of current, so that's an SI unit. So it's a movement of charge. That's what we call current when we talk about electricity. When charges start to move, we call it an electric current. The unit for that is the ampere. And then we have luminous intensity, the unit of which is called a candela. And I didn't write them on the board because we don't need them yet. You know, in chemistry and in core physics, these are absolutely the most important units that we're going to use. So these are called the base units. A meter is this big, kilogram is something you can hold in your hand, a second is something like this, you know, kind of a nice ticking of the clock that you already know. And the mole we'll talk about later, and temperature we're going to talk about a little bit later as well. So we have these as the base units. Now, there are also units called derived units, and I haven't written them on the board. All the other units that we really use in life are called derived units. In other words, they come from the base units. So these are the base units, the fundamental units, but we also have units like, I'll just write a couple of down. I guess I could just do it right here. What about the unit of velocity or speed? Meters per second. You see, this is a unit, meters per second, that is made by taking the distance you travel divided by the time it takes to go that distance. So notice that meters is a base unit and seconds is also a base unit. You put them together and you can get a new unit called meters per second. But that meters per second, it's not a fundamental unit, it's a derived unit. It comes from the simpler units that I have on the board here, right? Another example of a derived unit would be, so I'll put speed here. Another example of a derived unit would be volume. Right? A volume might be represented in cubic meters or maybe even cubic centimeters, and we're going to talk about centimeters in just a minute. But when you take a cube, and you 1 meter on each side like this, then it's a unit of volume. One little edge here of every cube is like 1 meter. It would be called a cubic meter, and it would form a unit of volume. That's how much space something occupies. But you see, the unit of volume is not a fundamental unit. It comes from the meter. And so it's a derived unit. And the last one I'll talk about here, and we'll get into this one in its own lesson as well, we have the unit of density. And we use that a lot in chemistry and physics. So the unit of density would be how many kilograms of mass something has compared to or divided by its volume. So kilograms per cubic meter, let's say. So if you have a cubic meter, literally a crate of cotton or something like, or water or whatever, then you measure its mass, how much substance is there, and then you divide it by the volume, and you get something called the density, which is a comparison of mass to volume. And so we'll talk about that in its own lesson. But you can see that kilograms is a base unit and meters is a base unit. And so by taking kilograms and dividing by meters cubed, we come up with a new derived unit. So these derived units, for the rest of our life, we're going to be dealing with derived units. I can go on and on and on. I mean, you can talk about the units of magnetic field. That's a derived unit. I can talk about the units of, I can talk about the units of acceleration. That's a derived unit. I can talk about the units of a force, newtons of force. That's a derived unit. All these equations that we use in physics and chemistry that involve these quantities, you get a new unit that comes out. It's a derived quantity, right? In fact, the unit of joules. We already learned the unit of joules. We talked about the unit of joules being a unit of work. It's also thought of as force times distance. You're taking two other things, multiplying them together, so that's a derived unit as well. So these are the core units. Now, these units are great for everyday use, but what if we have very large distances? Then the meter isn't really helpful, or very, very small distances is what we're going to mostly be doing in chemistry. So if we're going to take these units, or any unit really, and modify them to make them bigger or smaller, we have what we call the metric system. Now this table is very busy looking, okay? It looks very scary at first, but don't worry about it because we're going to go through them. But also, even though I give you the full table here, and if you open up your whatever book you're using, there'll be a table of metric system prefixes like I've put here. But really and truly, we only use a few of these out of the table on an everyday basis. Most of them we don't use in an everyday fashion. I'll circle the ones that we use quite a bit. So let's go through what this thing is actually telling me. All right. So what we do, first of all, I've used the idea of a watt here. And I could have used meters, or I could have used seconds or something, but I used watt just to do something different and to show you that it doesn't matter what unit we're talking about, we can always attach a metric prefix to it to make it either bigger or smaller. Now, a watt is something you do have familiarity with because the old incandescent light bulbs, the ones that glow, and get warm, typically in a home, typically it's around 60 watts. So you have an everyday familiarity with how much energy is coming out of a light bulb, because 60 watts is 60 joules per second. The watt is a unit of energy flow. But anyway, you've seen a light bulb. You know how bright it is. So you know roughly what 60 watts feels like and looks like, okay? But what if you want to talk about a nuclear reactor? It's way more than 60 watts, and you don't want to write a gigantic number down, so we use these metric prefixes. All right? Let's talk about giga first, because that's easy, right? So here's 1 gigawatt. The metric prefix for that, we call it giga when we say it out loud. We attach the prefix giga to the unit gigawatt, and we abbreviate it with a capital G and a capital W, and giga means 1 times 10 to the 9, which is a billion watts, right? So when you use the word giga, you are telling the person that you're talking to that giga means 1 billion, because 1 times 10 to the 9 is, when you move the decimal point 9 places to the right, it reveals that big number there. And so that is 1 billion, right? So when you say 1 gigawatt, or in computer terms, we talk about gigabytes. That's 1 billion bytes, right? And so we don't have to write the big number out. We just talk about a larger unit. What if we have 1 megawatt? Nuclear reactors are often measured in megawatts, or some kind of power plants are measured in megawatts. So that's 1 times 10 to the 6, which is 1 million watts. All right. What about kilowatts? Typically, the energy in the house is in the kilowatt range. So you're generally the power that your house is consuming in the kilowatt range, and that's thousands of watts, and it's abbreviated with a kW, a lowercase kW. So every metric prefix here has you attach it in front of the unit, and it changes kind of the size of the unit you're talking about, and it also has an abbreviation. So let's go back up to the top. We have peta for petawatt. This is a unit we don't use too much because it's so gigantic, but it's capital PW. Terawatt, again, a very, very large unit. We don't use it too much. If you're talking about the sun or something, you might talk about terawatts, or some other phenomena. We don't typically build reactors in that range, but you could express it in terawatts. Then we have gigawatts, megawatts, kilowatts. All right, let's pause for a second before we go on any further. This expression of 1 times 10 to the 3, what does that mean? So let me go down to the bottom here. When we say 1 times 10 to the 3, that's a kilo, or whatever it is, kilowatt. From scientific notation, that means you take the decimal point here and you move it 3 spots to the right. So you have to put the zeros there. If the decimal point was after the 1, times 10 to the 3 means you move it 1, 2, 3 positions to the right. That's why it means 1,000. So this is kilo, means 1,000, right? What about, let's go up to mega, means 1 times 10 to the 6. So if we have mega, that's 1 times 10 to the power of 6. And that is the same thing as 1,000,000. So that's a million. How do you know? Because the decimal is here after the 1. This is telling you move it 6 places to the right. 1, 2, 3, 4, 5, 6. So it's 1 million times bigger. So this is mega. All right. So these large prefixes, the kilo, the mega, the giga, the tera, the peta, they're used to express big numbers, right? Because you have large amounts of energy. But keep in mind that I'm talking about watts here, but we could talk about kilobytes, megabytes, gigabytes. We could talk about kilometers, megameters. We could talk about gigameters if you want to. We could talk about, any unit we want, in seconds. We can talk about kiloseconds or megaseconds. When we do that, we're just taking the base unit that we had on the other board and we're making it bigger, right? In this case. Now, when we get down here, where the exponent gets down here, we jump to negative exponents. Now, it may have been a while since you looked at negative exponents in math, so we're going to talk about it here. But you can see that all of these exponents that get beyond this point are all more and more negative. What does that mean? So we're going to go over here and talk about that. We'll just give like one little example. Let's talk about probably a very common one, a milli. We'll talk about milli, meaning milliwatt, lowercase m, w, and it's 1 times 10 to the minus 3. What does this mean? So 1 times 10 to the minus 3 is a milli something, right? Well, if you remember, which is the same thing, by the way, as just 10 to the minus 3. Now, if you remember from math, when you have a negative exponent, what it means is you bring it in the denominator of a fraction. So it's 1 over 10 to the power of 3, which is the same as 1 over 1,000. So you see what I did here? When it's 10 to the power of 3, it's kilo, which makes it bigger by 1,000. But when it's 10 to the minus 3, it becomes 1/1,000th. That means 1,000 times smaller. So when you talk about a milliwatt, it's 1,000 times smaller than a watt. When you talk about a kilowatt, it's 1,000 times bigger. So the kilo here and the milli here, they sort of go together. Kilo means 1,000 times bigger than a watt or bigger than a meter. And 1 millimeter is like 1,000 times smaller than a meter. So if you look at a meter stick and look at the tiny little markings in there, there are 1,000 of those millimeter markings that are all the way from one end to the other of the meter stick. So a millimeter is 1/1,000th the size of a meter. So it's good for expressing small distances, like maybe the distance between, the thickness of my fingernail, or maybe, the thickness of my hair, or something like this, or it's just something small that I can hold in my, maybe a couple sheets of paper would be a fraction of a millimeter or something like this. And notice that as the exponent gets more and more negative like this, so this is 1/1,000th of a watt, a microwatt, which has a symbol mu. This little Greek symbol, Greek letter here is pronounced mu. So we don't want to use m because we also already have an m for milliwatt. So we have to have another symbol. We call it mu. This is microwatt, is 1 times 10 to the minus 6, which means 1/1,000,000th of a meter. Because notice, if it's 10 to the 6 up here, 1 megawatt is 1 million times bigger than a watt or whatever it is we're talking about. And then a microwatt is 1/1,000,000th the size. So as you kind of march across this table, they kind of go in pairs. And some of the prefixes make it like 1 million times bigger, and the opposite prefix makes it 1 million times smaller. Let's go up to giga. Gigawatt is 1 times 10 to the 9. That's 1 billion times bigger than a watt, or 1 billion times bigger than a meter, or whatever. But if we go down here to 10 to the minus 9, it's called a nanowatt. And that is 1 billion times smaller than a watt, or 1 billion times smaller than a second, or 1 billion times smaller than a meter, and so on. So that's how this thing works. And you can kind of look at this table and kind of like, you don't really need to memorize anything, but let's just kind of go from top to bottom. The largest unit that we're going to learn about is called a peta. So petawatt, PW, and that's the exponent, watts. Then we have terawatts, 10 to the 12. Then we have giga for gigawatts or gigameters. That's a billion times bigger. Then we have megawatts or megameters or whatever it is, which is 1 million times bigger. Then we have kilowatts or kilometers, lowercase kW, that's 1,000 times bigger. Then we start getting to the smaller units. 1 deciwatt or 1 decimeter, 10 to the minus 1. It just means it's 10 times smaller. 1 centimeter or centiwatt is 100 times smaller, because this will be 1 over 10 to the power of 2. That's 1 over 100 times smaller. Then we have milli, which is 1,000 times smaller than a watt. Micro, which is 1,000,000 times smaller than a watt. Nano, which is 1,000,000,000 times smaller than a watt. Pico, 10 to the minus 12, which is, I don't have a word for it, but that's that much smaller. Femto, 10 to the minus 15. Now you're starting to talk about on the scale of atoms here. These units down here, the picos and the femtos, if it were in meters, you'd be talking about the actual size of atoms. The smallest we have here is atto at 10 to the minus 18, and zepto, 10 to the minus 21. Now, I told you some of these are more useful than others. I'll show you the ones that we use all the time. We use kilo all the time. We use mega all the time. We use giga all the time. We use those in everyday language. Gigabyte, megawatt, kilowatt, kilometer. We use those all the time. We also use centi all the time. We also use milli all the time in everyday life. Now, because we have centimeters and millimeters, right? Now, we also, in chemistry and physics, we use micro all the time, because when you get to small scales, we use this a lot, often. And in chemistry and physics, I'm not going to circle it, but nano and pico, we actually use those a bit as well. Nano a little bit more, because this is starting to get into the scale of the size of the atom. These other ones down here, the atto and the zepto and all that, we don't use them too much. And also up here, the peta and the tera, we don't use them too much. So really, it's a gigantic table, but there's only like 5 or 6 of them that we really use with any kind of like regularity. All right, so I think what I want to do now is solve a couple of problems. They're very simple. They're going to take like no time at all. So what I want to do is go over here, and I think I want to write down an abbreviation, and I want us to figure out what the exponential notation would be for that, right? So what about D? So D means you got to go look at your chart. D is for deci, right? You go look at the prefix. Which one is D? That's the only D I see, and that stands for deci, and the exponential notation is 1 times 10 to the minus 1. So the answer to this would be 1 times 10 to the minus 1, and it's deci, right? Now the next one I have here is C. What is the prefix for C? Well, C is for centa, right? Centiwatt, centimeter, centisecond, you could even say. That's 100 times smaller than the base unit. And so it's 1 times 10 to the minus 2, which is 1 over 100. And of course you pronounce it, or you say centi right there. So we could say 1 times 10 to the minus 2, and that stands for centi. We're just getting a little practice with, figuring out how to use these things. The next one is F. This is one we don't use too much, but where is F? We look down here and we see F is way down here. It's a femto. That's what it is, femto. And femto, like femtowatt, is 10 to the minus 15. So it's 1 times 10 to the minus 15, and that's femto, right? Next one, D. We have this weird symbol. You kind of write it as, it's like a U with like a kind of a weird tail on one side. This is called the Greek letter mu, and it stands for micro. We can't use M here because we already use M for milliwatt, so we have to have another symbol. It's called mu microwatt. The way you say it is microwatt there. So it's micro, and that's 10 to the minus 6, which is 1 million times smaller, because that would be 1 over 10 to the 6, which is 1 over 1,000,000. So we say 1 times 10 to the minus 6, and that's micro. All right, so let's go over here, and we'll switch colors, and we'll go do E. And E, well, I shouldn't say E, sorry, that's not my actual symbol. I want to talk about the prefix M. M is up here for mega. Capital M is megawatt, right? Or megameter, or mega whatever, megasecond even. So m is mega, and it's 10 to the power of 6, which means 1 million times bigger. So it's 1 times 10 to the power of 6, and that's mega. Okay. Next, we have the prefix K. We go down K. K stands for kilo, kilowatt, kilometer, kilosecond, things like that. It's 1,000 times bigger, 1 times 10 to the power of 3. 1 times 10 to the power of 3, and that's kilo. And then we have G, almost done here. We have N. What do we have for N? N, we go all the way down. There's M. That's not right. N is for nano. Nano is 1 times 10 to the minus 9. That's 1 billion times smaller than the base unit. So 1 times 10 to the minus 9, and it's nano. All right. And then we have finally M. M is for milli, which is 1,000 times smaller, 1 times 10 to the minus 3, like millimeter, 1 times 10 to the minus 3. That's milli. And then I is our last one, P. What is the metric prefix for P? That's pico, picowatt, picometer, picosecond, that kind of stuff. 1 times 10 to the minus 12. So 1 times 10 to the minus 12, and that's pico. All right. So that was just a straight problem where we're practicing the metric prefixes. The next problem, what we want to do is I want to rewrite these numbers in terms of the correct unit. So let's say I give you 1.20 times 10 to the minus 9, and that's in terms of meters. So this is a very small number because you take the decimal here and you move it 9 positions to the left. If you are uncomfortable with scientific notation, go back to my lessons on scientific notation. I have great extensive lessons in that, in the math portion here. So you kind of need to understand scientific notation. When you have a negative exponent, power of 10, it's taking the decimal and moving it 9 positions to the left. So this is a really small number. The actual number is 1.20 times 10 to the minus 9. So we go over here and say, well, 10 to the minus 9 is what we call a nano something. So what we're talking about here is not watts, but it's nano means 10 to the minus 9. So since this is 1.20 times 10 to the minus 9, what we say is it's 1.20, and then this whole thing can be replaced with nanometers. So 1.20 nanometers, right? And the way you read this is 1.20, the nano means 10 to the minus 9 times 10 to the minus 9 meters. It's a very small unit of meters. The prefix is what kind of takes the place of this exponent here. This is much easier to write than this in calculations, but they mean the same thing. All right, the next one. What about 2.20 times 10 to the minus 15, and this is going to be seconds. This is incredibly short time scale, because what this means is I take this decimal and I move it 15 positions to the left. This is an incredibly small number. 10 to the minus 15 corresponds here to the prefix femto, but we're not talking about watts, we're talking about seconds, so we can express this as 2.20, and this is femtoseconds, so Fs. And this means 2.20, the femto means times 10 to the minus 15 seconds. And so these are equivalent. Okay. The next one, what do I have for my next one here? 1.50 10 to the 9. 1.50 times 10 to the 9, and I'm talking about grams. 1.50 times 10 to the 9 grams. 10 to the 9, not to the negative 9, 10 to the positive 9 is giga. It's gigabytes, gigawatts, gigameters, things like this, 10 to the positive 9. So what I have here is 1.50, and the times 10 to the 9 gets replaced with a gigagrams. All right, so this is 1.50, this means billion grams, times 10 to the positive 9 grams. And then we have finally D, our last one, 3.50 10 to the 6. 3.50 times 10 to the 6, and the unit I'm talking about is liters. We haven't talked about liters yet. We're going to talk about that very, very soon, but this is a unit of volume. You buy a liter of water or something like this. The exponent here is 10 to the power of 6. 10 to the power of 6 is right here. It's mega, because the word mega means million, essentially, 10 to the power of 6. So we replace this, 3.50, instead of times 10 to the power of 6, we just write it as megaliters, because this is millions of liters, millions of liters. So 3.50 megaliters. All right, now we're almost done. Almost done. Just get a little more practice with this. In the next problem, what I'm going to do is I'm going to write the following down, 4.50 nanoseconds. And I want you, or us, to convert this back into the best exponential notation, scientific notation, right? So we're going reverse. Instead of going this way, we're going the opposite way, 4.50 nanoseconds. So what does this mean? 4.50 times 10 to the power of what? What does a nano mean? Nano means 10 to the minus 9. So we write it as 10 to the minus 9 seconds. The nano means times 10 to the minus 9 seconds. So that's the answer to this one. All right, the next problem I want you to pay extra attention to, 18.0, and it's going to be FS. That's femtoseconds. How do we convert this to exponential notation, or scientific notation is really what I want. So it's going to be, let me show you the way I would do it. It's going to be 18.0 times 10 to the power of what? F is for femto, right? Femto is right here. That's 10 to the minus 15. So that's minus 15 seconds. Now you might say we're done, and this is correct. This is actually equal to this, but I want you to write it in scientific notation. Scientific notation means the decimal point always comes after the first number. The decimal point is always after the first number in scientific notation in all of these cases. But here, because there was 2 digits here, I wrote it as 18.0, and I have 2 digits here. So what you need to do is, I'm going to switch colors here. What you need to do is basically move this decimal back. So you make it 1.80. The same digits are here. You move it back 1 position times 10. But because you moved it back 1 position, you have to modify the exponent. So see, what this means is it's 15 decimal, we move the decimal 15 positions to the left, but since I already moved it 1, I only need to make it to the minus 14. So 14 to the left from here, 15 to the left from here, that's going to give me the same number, and that is the answer right there. So that is kind of a tricky question. When I give you something and say write it in scientific notation, you can't leave it like that. You have to write it down as you see it, and then move that decimal 1 position, and then alter the exponent so that, because if you move it 15 from here, it's going to be too small. You have to change it so that it only moves 14 positions. So 1.80 times 10 to the minus 14 seconds. All right, let's take a look at the next one. We have the same thing going on, 128.0, and it's picometers, right? Pico. So what I do is I say, well, that's 128.0 times 10, and what does pico mean? I go over here to pico, pico watt, pico meter, whatever it is, it's 10 to the minus 12. 10 to the minus 12, and we're talking about meters. So this is 128.0 times 10 to the minus 12 meters, but it's the same problem. I want to write it in scientific notation. So this decimal needs to move 2 spots to the left. So in scientific notation, 1.28, you can drop that last 0 because that doesn't matter. You could write it there, 1.280 times 10. Now, because I moved it 2 spots to the left, when I need to alter the exponent, and it's going to be minus 10, right? Because when the decimal was here, it's moving 12 positions to the left. Since I already moved it 2 spots, I only need to move it using the exponent 10 positions to the left for these to be the same. So this is meters. This is the final answer, 1.280 times 10 to the minus 10. Make sure that looks a little bit like a 6. That's a 0 right there, meters. All right, now here's our last problem of this type, D. It's going to be 35.0 micrometers. Remember this little symbol here, mu, it stands for micro. So what I'm going to write this as is 35.0 times 10. And what does micro mean? That means one microwatt, micrometer, microsecond. That's 1 million times smaller, 1 millionth. So 10 to the minus 6. And we're talking about meters right here. Same problem though, because I want to write it in scientific notation. So because the decimal is here, I need to move it 1 spot to the left. So it's going to be 3.50 times 10, and I need to alter this to only move it from this position 5 spots to the left to match the 6 spots from the left there. So 3.50, or 3.5 times 10 to the minus 5, and this is in terms of meters. All right. We only have one more little question. I promise it's very, very short. So let's go back over here and just do our very last problem, which is just going to be a couple. And the question is, what type of measurement does each unit correspond to? So pico or PS here. If I just say, you know, we have 4 PS, what kind of unit is it? Is it length? Is it time? Is it distance? Well, the way you read this is you go and say, well, the base unit is second, the P is pico, right? Because P is pico, and so that's picoseconds. So the unit that we're really talking about here is time. I just want you to tell me what type of unit is it. Okay, what about the next one? M. Well, we see at M, that's going to be meter. N is going to be nano. Nano, we can just look and check at our chart again over here. N here for nano, and that's 1 billion times smaller, so that's nanometers. So this is billionths of a meter, and this is length. It's a very small unit of length. And then the last one here is just K, which we talked about in the beginning. K is the SI unit for Kelvin, which is, or temperature, which we call the Kelvin temperature scale. So anytime you see kelvins, then you know it's temperature. All right, now that's it. So in this lesson, we've done quite a bit. We've introduced the base units in the SI system. We talked about the idea of having derived units. So we have the base units, which are fundamental, and then all the other units are made of combinations of the base units, kind of like sticking them together like Legos in different ways, and like meters per second and things like that. They come from the base units. And then we talked about the metric prefixes, which take those base units and modify it, either make them bigger or make them smaller. And it all comes back to powers of 10. It's all powers of 10, and the reason why it's powers of 10 is because the power, when you multiply by a power of 10, it either moves the decimal one spot or however many spots to the right, or if it's a negative exponent, it'll move it the other way and make the number smaller by moving the decimal point to the left, right? And then we did problems just to get practice with this. So I'd like you to go through these again. Make sure you understand the metric prefixes. Most importantly, just keep in mind that even though we have them all here, most of the time we're going to use the ones that are circled here. Occasionally you'll use other ones, but these are the most common. So study this, make sure you understand, follow me on to the next lesson. We'll continue to build your skills. Learn anything at mathandscience.com.